Welcome to Brain Vision.
We will start from the equation that relates velocity of the wave propagation with the force of tension and the linear density. Now, from this equation, we will transform it by raising both sides to the power of 2 and algebraically changing the sides of certain terms. So in this case, F will be equal to velocity squared times the density. Now, in this problem, we have two forces. We can say that we have force F1, which will be equal to velocity 1 squared, and the same density, and the different intensity of the tangent force that corresponds to the different propagation velocity times the linear density, which stays the same in both cases. So how this change in the tangent actually relates to the change in the different temperatures and also to the rest of the variables. We can see that from the formula which relates the force of tension to the Young's modulus. So the change of the force, which is F2 minus F1, is equal to negative A times Young's modulus times alpha times delta t, where alpha is the coefficient of the linear expansion due to the change of temperature. And also notice that this formula actually is derived and relates to the formula of the change in length due to the change in temperature. So from this expression, knowing that generally speaking, F over A, or the pressure, thermal stress, which is in units of pressure, is related to the Young's modulus. In this way, we can see that we derive this formula from this formula. So this is just F, negative A y alpha delta t. This is how this formula is derived. And we just say, okay, this F here is going to be equal to the difference between the two tangent forces that is corresponding to the change of the temperature. So further, we can substitute the relationship between the forces and the velocities. So further, we see that we have that v2 squared negative. We can immediately factor out this negative, which will be positive when factored out. So this is the density and velocities being subtracted, squares of velocities, which equal to negative A y alpha delta t. Now, why we needed this equation here? Well, we need to somehow relate the length and this alpha constant. So clearly, from that formula and from here, we can, from this expression here that we obtained, we can say that alpha equals y and then velocities, or the linear density times the velocity difference, propagation velocities, over is going to be negative A Young's modulus in the change in temperature. So knowing that, and also remembering that expressions for densities are like this, and that basically this can be substituted, and we can say it is actually this. We obtain that further this coefficient equals we have linear density and the area, so immediately we can substitute for just the density, so minus density, the difference in propagation velocities, Young's modulus, and the change in temperature. And this is the final answer for this problem. And look how we can use the change of, when we have this case like two rigid supports and the temperature T, and the temperature T changes, and now we have immediately we have some change in the thermal stress, and we have the change, of course, in the force, the normal force, and this normal force is related to the velocity of the wave propagation. So if we measure velocity of the wave propagation, we can actually determine the change in for example, coefficients, or we can, if coefficients don't change, and if we hold them constant, then we can find the change in the temperature, knowing the change in the wave propagation, but the change of squares. So that is just one note for the end of the problem. I hope you find this helpful, and I hope to see you in another lesson.